So here are some more, not properties, but here are some tools of integration. So integration tools. So the first thing is that we can reverse the order of integration because, you know, that's the way we roll. So we can reverse the limits. It's called the limits of integration. So the numbers you see on the side, or the letters if we're working with variables. So by reversing that, what we mean is, what we could do is if we have from b to a of f of x dx, so here we would integrate from b to a, but if we wanted to reverse those, we would just flip them, okay? We're going to flip them and add a negative sign in front, okay? So this is equal to, so this thing here was equal to negative, and we're going to switch those, we're going to swap those limits of integration, okay? So something like that, all right? So we can just do that nilly-willy if we feel like it, or if the problem calls for it, okay? The next thing that I want to say is that if we're integrating on an interval, so the next thing is going to be if we're integrating on the interval a to a. So let's look at that graphically. Let's say we have some function, all right? We're going along, okay, here's our f of x, here's a, and we want to integrate from a to a. All right, so that is it. Real exciting, right? So we do get a length here, like a height, but we have no area. So that means that the integral from a to a of our f of x dx is always going to equal 0, a big fat 0. The next tool of integration is called additivity of adjacent intervals. Okay, so adjacent intervals. All right, so what does that mean? So let's look at it. So additivity meaning you can add it, and then adjacent meaning next to or neighboring. So I'll just say next to, okay? And then intervals meaning intervals, basically. So what that means is that on a graph, let's say we have our x and y, okay? Here's our function. I like how all my functions look the same. Anyways, so there's our function. Let's say here's a to b. Here's a, b, and c, all right? So let's say we're integrating from a to b first, all right? So this is the area here. So if we're integrating from a to b, our function f of x dx, that's what we would get. We would get that area in the shaded part right there. And then let's say we integrated from b to c. Okay, so this would be this new one. I'll put the lines going this way. Okay, so that would be b to c. So b to c, and that would be f of x dx in the integrand. Okay, and basically what that means, if we compute these areas separately, and because they share the same wall, which is the b, right, the b here as one of the limits of integration, that means when we add them together, we're going to get the total area under the curve from a to c. So we can kind of just, this line here disappears, okay? So that's basically what it means. We can do that. We can just either split up an integral into different intervals, or we can combine intervals as well if they're adjacent to each other. Alright, so let's do an example of some integration. So what we're going to do is calculate the following integral. So from 0 to 2 of 5x to the third minus 4, and then dx. And then we're going to use the formula, so using the fact that from 0 to b, integral from 0 to b of x to the third dx is equal to b to the fourth over a 4. Okay, so what we want to do is get this in the form where we can use this formula here, what we're given, okay, to solve for the integral. So the first thing that we're going to do is apply some of the things that we know. So the integral from 0 to 2 of 5x to the third minus 4, and then dx. So first of all, we see this negative sign here, which is basically like adding a positive, or adding a negative of something. So what we can do is basically just break out the integral with that subtraction sign. So we have 0 to 2, integral from 0 to 2 of 5x to the third dx, and then we can have that subtraction sign in the middle, splitting them up, and then integral from 0 to 2 of 4 dx. Okay, so now what we can see is that we have a constant here, right? This constant 5, so according to the constant multiple rule thing that I just kind of made up the name for, but it is a constant multiple, right? So we can bring that out. Basically, that's like our c. So if we do that, we can have 5 times integral from 0 to 2 of x to the third dx minus integral from 0 to 2 of 4 dx. Okay, so now we note something else. So first of all, this is in the form of this, right? So now we can use our rule for this one. All right, and then also we can deal with this one separately at the end. So then we have 5 times, so according to the rule, we have integral from 0 to b, so 2 is like our b, right? And then x to the third dx, so this should be equal to b to the fourth over 4. So instead of b, we're going to plug in a 2. So we get 2 to the fourth over 4, and that's going to be minus, and here, now let's deal with this. So we have some integral of a number, and this is a constant, right? So remember that the integral of a constant is just going to be that constant times b minus a, so that'd be 2 minus 0, right? So we're going to write that here, 4 times 2 minus 0, all right? So then we get, let's see what we get when we simplify. So this is a 5 times 16 over 4, so that's a 4, minus 4 times 2, so this is equal to a 20 minus an 8, so our final answer is going to be a 12. Alright, so our last topic for this video is going to be about integrals, so the things we've been learning about, right, involving inequalities. So inequalities. Alright, so the first thing that we're going to start with is called the comparison theorem. So comparison theorem, so I'll just abbreviate theorem. Okay, so basically what that says is if our f and g are integrable, I think integrable sounds good, integrable, and if our g of x is less than or equal to f of x for x in a b in the interval, then that means then we have that the integral from a to b of our g of x dx is going to be less than or equal to the integral from a to b of f of x dx. So here's the reasoning behind it. So let's say we have something going along, right? So here's our x and here's our y. Here's f of x, okay? So there's f of x, and here's g of x going along, right? So there's our g of x. So this means this is the condition, right? So they're both integrable, and g of x is the lower function. It's always going to be below our f of x. It could even, we could even have an example here where it does touch at one point, okay? So it touches and then it goes back down. This would be the or equals to, right? The equals to part. But anyways, so it just look like that. But in any case, so we'll deal with the left one because that's a little bit more clear. From a to b, so here's a and b. If we take the area under the curve of both of them from a to b, then our f of x up here, that's always going to have a greater than or equal to area than g of x, which is just the small area down there. Okay, that's all it's saying, is if f of x is always a greater function than g of x, then it's always going to have a greater area under the curve. Okay, so this is the comparison theorem, and now let's go over kind of like an offshoot of the comparison theorem.